Hello everybody and welcome back to, I guess this isn't the final video I'm making for fundamentals, but the video for your final exam is already out, so this is the final one I'm recording this year. This is your exam 3 review video. I'll be working through all the problems in 2023, kind of explaining some of the tips and tricks I use to do well on this exam. But yeah, without further ado, let's jump into it. So this first part of the exam is a lot of math. Some of the problems are easier than others. Usually the exam starts off a little bit easier. This first problem is no exception. So how do we set this up? Freezing point of an isoosmotic solution. So for this, you basically need to know two things. You need to know the freezing point depression equation is 1.86 times your number of osmoles, which in this case is 285 milliosmoles osmotic solution, right? So that is 0.85 regular osmoles. Multiply these, we get 0.52. Pretty easy, right? One-step multiplication. You shouldn't get that wrong. For this next one, it's a little bit tougher. So we have osmotic pressure for a 1% solution. When I see 1% solution, I immediately write down something to the effect of 10 milligrams per milliliter. Right, you could also do something like 10 grams per liter. Doesn't really matter. I'm going to keep them milliliters for now, and I'll show you why a little bit later. But essentially, we want to find osmotic pressure. Okay. So what we do from here is we need to get this in osmolality, right? And to do that, we need moles. So what we can do is we can use our grams per mole. We can do 1 millimole of calcium chloride is equivalent to 111 milligrams. And then this will get us a value of 0.09 millimole per milliliter. From here, what we can do is we know there's 3 ions, right? Because 2 chlorides, 1 calcium, these will all break up. This is an ionic bond. So we'll do that 0.09 with 3 ions. What we'll do next is we know our G coefficient, our osmotic coefficient is 0.88, so we need to factor that in, so times 0.88, make that value a little bit lower. And then we'll get a value once we plug all these in of 0.09 times 3 times 0.88. So it'll get us a value of about 0.24. The last thing to multiply this by is our osmotic pressure coefficient. Now this is at 25 degrees Celsius, so if you remember, this is 24.4 atm times our 0.24, and when you solve all that out, you get 5.8. So again, sorry, which is C. So a bit more work to that problem. Pretty easy though. The main problem was just getting this into osmolality. But once we could do that, we knew the number of ions and we could kind of just multiply it through. This next one, it's pretty simple actually. We're essentially just solving for the osmolality of a substance in solution. So we know that there's 0.01 mole NaCl, and this will split up into 2 ions eventually, so we'll factor that in 0.5 liters of water. Then we also know that there is a another form of it in here somewhere. Because weak acid. Oh, okay, I see how I set this up. Sorry. So this has a pKa of 6. Solution has a pH of 4. This isn't going to dissociate super readily, right? It's going to primarily stay in this HA form. So we're just going to assume this all stays intact. So we also have 0.01 mole of, we'll just write it as HA. And then from here, we multiply all this by osmotic coefficient, right? Kind of bread and butter to a lot of these problems. When we do this, we get, I'll plug it in the calculator. It doesn't really matter too much since we have it in front of us, but I'll do it just for fun. Times 2.04 here, and then 0.01 here over 0.5, get 0.02, and then 5 times 0.96 times 100. Yep, and we get that 57. So again, just another matter of multiplying all this through, but once you get it, you get it. So the answer for that one was indeed your 0.9 or 0.5. Did I do this backwards? No, sorry, I was reading 0.96. Duh. I've got a piece of paper to my side where I have all this work written down. This next one you don't really need to do math for. And this is kind of a logic problem. There's one like it every year. So essentially, you have pharmacy tech. It's changing the pH of a solution from 8 to 7.4. This is really not a lot of hydrogen atoms, right? If this was a lot of HCl, this could potentially change the osmolarity, but since it's so low, it doesn't change it. The other key to this problem is this is an isotonic solution, right? So we have an osmolarity of 285, or 0.285 osmoles. This one's milliosmoles. So essentially what we just do is, since there's such a minuscule change, it'll be slightly higher than this, but really not higher at all. And 0.285 rounds to 0.29, and that's pretty much all there is to that one. This next one, not too bad, all things considered. It's essentially, we're looking for a difference in osmotic pressures. And we know that inside a drug capsule, right? So water doesn't rush into it too much. We need to find a way to balance these pressures. So there's a really easy way we can set this up, actually. We just have to find each individual osmotic pressure. So to do that, we do our concentration, so 0.35 molar of NaCl. We know there's two ions, right? There's a sodium and there's a chloride. So we multiply this by 2. Osmotic coefficient, we always need to have it, so we multiply this by 0.9. And then finally, our pressure value. This is what we've used before. It's that 24.4 atm times 24.4. Then we need to subtract from the pressure on the outside. This is 0.15. So 0.15, again, it is NaCl. So we have two ions that it'll split into, again, times 0.9 for that osmotic coefficient, times 24.4. When we solve all that through, we get a value of 8.8 atm. So for this final problem, not too bad, again. Essentially, the key to this is being able to recognize, in order to find the osmolality, we need to be able to recognize two things. And the first thing is that this is a drug suspension. And anything that is a particle or a solid in a suspension does not contribute to osmolality, right? Because it's kind of just floating around in solution. It's not dissolved. It doesn't add anything else. So it's only the drug in that's kind of soluble in the suspension, which we have is 12 milligrams per milliliter. So that's the first step to this, 12 milligrams per milliliter. And the next step we need to know is molecular weight of the drug. So we can convert this to moles. We need osmolality. And this is 276 milligrams per millimole. We also know that since this drug is the salt formula drug, it's NaD-. This will have two ions. And then we also know our osmotic coefficient is 0.94. Now you might notice that this is milligrams per milliliter right now, as well as millimole. We actually will not need to, these milligrams will cancel. But since we're going to try and get this into osmol over kg, that's equivalent to millimole over milliliter. The units are obviously different, but you basically multiply by 1,000 and divide by 1,000. So we can actually just leave our numbers like this. It's really easy. And once we solve all that out, do this math right here, right? What's in this box? Sorry, I know I've written all over the place, but what's in this box right here, you do all that math you get a value of 0.08 osmoles per kilogram. Okay, let's keep going. So for this next one, we're essentially trying to find out sort of the osmolarity of a solution again. So not too crazy. The key to this problem is just knowing how an acid behaves in solution versus how a salt behaves in solution. So we have two things in the solution. We have 0.01 molar acetic acid, which is our acid obviously, and 0.03 of sodium acetate. So essentially what we're trying to solve for here is to see if the acetic acid will dissolve or not, and it will. But kind of the key to this problem is just to recognize that the pKa of the solution, even though it's 4.8, the pH of the solution is somewhere in here. I believe it's 6. I can't find it right now. But essentially, the key to this problem is understanding that that's not going to make a huge contribution to the change in the solution. So when we're thinking about the osmolarity of the acetic acid, we can just estimate it to be 0.01 because we don't expect this to change, right? So up here, this isn't going to dissolve enough, dissociate enough to make a real meaningful difference. So we can do 0.01 plus 0.03 of our sodium acetate. But since we have to multiply this by 2, right? Because 2 components, sodium and acetate. So we can multiply this by 2. And then we simply finish this off by osmotic coefficient again is 0.95. So multiply all this by 0.95. And when you do that, you get around 0.067. So this next problem isn't too bad. It's essentially, the key to it is recognizing what would neutralize an acid in the stomach, and what would actually neutralize the acid itself isn't the aluminum hydroxide or the magnesium hydroxides, it's the hydroxides themselves. So aluminum hydroxide has 3 hydroxides to neutralize an acid with, whereas magnesium only has 2. So how do you set this up? If we have 300 milligrams, we have 0.3 grams of aluminum hydroxide divided by 78 grams per mole. And then we'll also multiply this before I add. We'll multiply this by 3 because the rationale for this is for each mole aluminum, or no, sorry, I have this written backwards. There's 3 moles of hydroxide for each mole aluminum hydroxide. And that's just how I'd write it out long form, but I'm just going to write it as 3 because that's easier. We don't need to think about these units, but that's essentially how it's working. Let's multiply that by 3 plus 200 milligrams, so 0.2 grams of magnesium hydroxide over 58.3 grams per mole. And then the last step is, since these are in moles and we want them in millimoles, just multiply these by 1,000. I think this one is like 11, this one's like 6 or something, maybe it's 7, but you get your answer of 18.44 when you actually solve the math. I think this one was 7, because otherwise it'd be this answer. It's not, it's E, I promise. For this next one, this one is sort of, it goes into your isotonicity, right, your E values. It's not incredibly hard. How I like to think of problems like this is whenever I see kind of a concentration of something, I like writing it out in the number of grams per milliliter or grams per liter. So if this is 1%, we know that there is a 10 grams per liter times 0.2 liters. So we essentially have 2 grams of the sodium benzoate. And then from here, what we have to do, we have to multiply 2 by our E value. It doesn't have the E value here, but it is 0.4. You would get this from a table normally. So 2 times 0.4, we do that, I believe that's 0.8. Sorry, I can't read my own handwriting. 0.8. And then what we have to do from here is find out how much sodium was originally in our solution. Well, how do we do this? Well, we know that sodium is 0.9 grams per 100 milliliters, multiply this by 200 milliliters, we get 1.8 grams of sodium. Our equivalence value is 0.8 grams of sodium, so 1.8 minus 0.8. We get 1 gram of sodium, and then there's one more step. This problem actually doesn't want a sodium solution, it wants a sucrose solution. But that E table, since it's all in values of sodium, we now need to go the other way. So instead of multiplying by an E value, like this 0.4, like we did up here, which is not circling for some reason. Okay, there it goes. We do 1 gram sodium divided by 0.08 equivalents of sucrose. We do that, we finally come to this final answer of 12.5. So again, we kind of had to go back and forth with that one a little bit just to get it in sucrose, but essentially if you're making things into sodium, you want to multiply, and if you're taking things out of sodium, you want to divide. I think that's the best advice I can give for that. This next one isn't too hard, it's just a little bit longer. Very similar to the last problem, we know we have 0.5 grams of phenobarbital, right, per 100 milliliters solution. And then we want 500 milliliters, so multiply this by 500. This is 0.5, sorry about that. We get a value of 2.5. E value for this is 0.24. We multiply all that out, we get a value of 0.6. For our streptomycin, 2%, so this one is 2 grams per 100 milliliters times 500 equals 10 grams. This E value over here is 0.07, it looks like. So we multiply all that out, we get 0.7 grams. And then finally, we need to find out what our sodium is, what amount is needed left to make it isoosmotic. So for that, we need to know what an isoosmotic solution is for this. So we have 0.9 grams per 100 milliliters sodium, right, times 500 milliliters. This is 4.5 grams of sodium, but we don't need to add a full 4.5 grams of sodium because we already have this many equivalents. So we subtract 0.6 plus 0.7, which are the things that were already added. When we subtract those, we get 3.2. Not too bad there. This next one can be shortcutted pretty easily, actually. We know that this morphine sulfate is already, it's not needed in this formulation, but assuming this is already isoosmotic in the solution, right? Because we wouldn't give this if it wasn't isoosmotic. And there's still this penicillin in here, so there's still other components in the solution. It wasn't just morphine that made it isoosmotic. Do a really nifty shortcut, actually. If we know that 0.5% of morphine made the solution isoosmotic, we can multiply by its E value, which is 0.14. And remember, this E value turns it into sodium. So essentially what we get is our answer is 0.07%. And that's it. That's the entire problem. This is the equivalent of sodium that would make it work. So a really handy thing with equivalence is if you're ever replacing a percent with something else and you're replacing it to sodium, all you have to do is multiply by the E value. You don't need to write it out like this. In this problem up here, we needed it in grams, but if we were substituting again, we could have written like this 0.05, for example. And that would have made our lives, or our 0.5, sorry. That would have made our lives a lot easier, but unfortunately the problem didn't let us do that. This next problem, it's a similar kind of idea. We have a solution that contains a drug, but we want to estimate the amount that we would need to add of NaCl to make it isoosmotic. So for this, we're expanding the solution, but we don't necessarily want to add more drug. We're just adding salt to get it up to where it needs to be. So if this solution is isoosmotic, we can assume that it's at 285 milliosmoles per liter. And then currently, or I'm sorry, the solution isn't already isoosmotic, but we're trying to get it there. So there's currently 150 already. So if we subtract 150, the difference we need to make up is then 135. Now, how do we do that? Actually, another really cool shortcut we can do here, since we know that one equivalent, or that this is just kind of a standard ratio, we know that 0.9% sodium is isoosmotic, and we also know that 285 milliosmoles are isoosmotic. This is essentially equivalent to writing 1 over 1, right? Because these values are both equal to isoosmolar. They would cancel each other if we converted these to like grams per milliliter, grams per mole. Whatever we needed to do, this cancels to 1. So it's essentially just a fraction, but we can cancel our units here with milliosmoles to find out what percent of sodium we need. So these cancel. And then when we essentially do this multiplication of 135 times 0.9 over 285, we get a value of 0.43% NaCl. So the last part of this problem that we need to do now is just simply knowing how much of the solution we need to make. We need to make a liter. So if 0.43 moles would work, we could use 0.43 grams per 100 milliliters times 1,000 milliliters, right? Because that's a liter. And when we do this, I'll do it over here, you get a value of 4.3 grams. So again, just another shortcut. I would recommend being able to know how to do this ratio, right? Knowing that you can write 0.9% NaCl over 285 milliosmoles. You could also, for example, if you were given a percent and you needed to switch, like let's say we were given 0.5% NaCl, you could also write it like 285 milliosmoles divided by 0.9% sodium. And then we could cancel these units. Because again, this ratio right here is just equal to 1 over 1. So that's a really helpful thing to remember. Okay, so these next problems are less math related, and they're kind of just a little bit of memorization, a little bit of common sense, and a little bit of luck. So for this first one, which of these should be isotonic? There's a slide somewhere in your notes that tells you which of these routes to memorize, but there's also a really good rule of thumb that I like to use in case I don't know. And think of it this way. Would putting a lot of salt in this area hurt? So for something like the skin, right, for a transdermal gel, no, I could have salt on my hand. For an oral suspension, could I have salt in my mouth? Yeah, it wouldn't hurt. It wouldn't taste good. And then nail plate, could I put salt on my nail? I mean, I guess. So really the only one that makes sense here is the eye, because I don't want to put salt in my eyes. Boom. This next one, memorization, right? This kind of goes back to the method I was talking about in the previous page with that 285 osmoles of sodium lining up with 0.9%. You could also do this with 0.15 molar. I can't imagine when that one would be useful, but you could do it. And then also this, there's a slide somewhere in your notes that has a list of these, but 0.3 molar boric acid is also equivalent to these. I believe it's used in eye solutions a lot. Don't quote me on that. But basically all of these are isotonic. This next question I did not like. I got it wrong. There is one slide in your notes that will tell you this. And essentially, when we think of these osmotic coefficients, right, we think of usually things, right, like salts completely breaking up, or at least primarily breaking up, because, you know, they have plus and minus charge, right? They dissociate in water. At really low concentrations, like this 0.0015 kCl, this actually is not the case. It will actually be equivalent to about 1. It will not break up in water, similar to dextrose, right? Because dextrose is a sugar, it doesn't break up. So for this problem, actually, number 3 is pretty much equivalent to 1. You can see that's twice here. But as we also know that for some of these bigger ions, their osmotic coefficients are a little bit lower. It wouldn't be as high as 0.82, so in this case, D. So again, if you see a really low concentration, it's probably 1. That was a problem that I think was the most missed in my class last year, so there's a chance he asked it again. For this next one, which of these is true? It's this one. Osmolarity is equivalent to osmolality in isoosmotic conditions. This is kind of like a rectangle square thing. Osmolality would not necessarily be equal to osmolarity. And I think the next problem even goes over that. We can go through the rest of these. Osmolality is related to dosage form. For example, a gel with high viscosity would have a higher osmolarity. That's not always true. Different substances could be different things. 305 is considered dangerous. That's not true. That's a range that can occur normally in our body. Calcium carbonate turns into CO2. That's not true. It would just not do that. I mean, I guess it could in a really acidic solution, but it wouldn't do that unless there is an enzyme. And then boiling point elevation is a common way to measure osmolality. That one is not true either. I believe that's measures something. I know freezing point depression can measure osmolality. I'd have to go back and look at that. That wasn't on this exam for you guys, so, or at least not in this exam, so I did not bother to relearn that. So it's C. This next one is also C. This is pretty important. You'll get math problems like this too. We kind of got one earlier with the suspension, and it's those oil particles in suspensions will not add to the osmolality, right? That's because these aren't technically dissolved in the solution. They just kind of exist in the solution. So that's this. And then for the rest of these, this is kind of that rectangle square thing we talked about. Isosmotic is not always isotonic. Mixing won't always keep it the same because chemical reactions can occur and change ratios of things. Solvent between solute and water, or normally stronger than solute to solute. This is not true. The solute interactions are usually stronger. And then osmotic pressure does not always include a semi-permeable membrane. It's just pressure on a container in general. So this one is C. And again, these are from the slides mostly. Usually these questions are reused though, like in this exam in 2022. So honestly, just memorizing some of these answers is probably the way to go for problems like that. This next one was new for our year, but it can be logicked out pretty easily. Why is citric acid so weird? Why isn't it a straight line? Essentially, which of these qualities does citric acid possess? So does it possess protons? Yeah, and these protons can dissociate. So likely 2 is an answer. Are there solute-solute interactions? Well, I don't know exactly what citric acid looks like. I know it has a carboxylic acid bond though. So just by knowing that, we can draw it out. We have a hydrogen bond here, hydrogen bond here. Okay, solute, check. And then for water, right, H2O. Hydrogen bond, hydrogen bond. So yeah, it's basically all of these. And just, again, you don't necessarily need to know what citric acid totally looks like. Just the fact that knowing it's an acid and also knowing it's an organic molecule probably means it's a carboxylic acid, like this, right? So you can kind of extrapolate that if you assume it's in water, which we could for this problem. Okay, these next few problems also aren't too bad. This first one, it's literally just asking how many solutes will this break up to into water. It actually breaks up into 3. It breaks up into 2 NAs and then an HPO4. Now, technically, some of this, hydrogen could dissociate. It wouldn't be substantial. And then whenever water breaks off into a solution, it's just more water. So it's not a solute. So we have 1, 2, 3. And there we go. This next one, whenever you see a reagent doubled, that's instantly second order. You can think of it since there's 2, there's second. That can cause some like exponential reactions. You can also think of this as since like technically these are all logs. This is like log A plus log A. This is more like kinetics math. It doesn't really matter. But essentially, right, we could also write this as 2 log A. And wow, that's exponential now, so it's second order. That's just a way to reduce it. So next one, not too bad. The important one to this is to know how zero order kinetics work. And essentially the half-life for a zero order kinetic is you would take your starting concentration, 1.2 milligrams per milliliter, divide by 2, right, because we want half. So now we have 0.6 milligrams per milliliter. Versus if we wanted like a third of this, we would divide it by 3, and that would give us like a 66% life. But since we only want a half-life, we could do that step to get half the concentration equals half the life, and now we just divide it by the rate, which is 2 times 10 to the negative 4, 2e negative 4. When we do that, we get 3,000 hours. It does what it in days though, divided by 24 hours, you get 125 days. Not too bad. This next one, I know there's some complex math you could do to solve this, but the way I like solving these pH problems is we have a pH of 5.2, and we know its shelf life is 9 months. And we know it is most stable at 3, meaning that as we get farther away from 3, the half-life is going to go down because it doesn't like it. This would also occur, for example, if we were at a pH of 2 and we wanted to take it to a pH of 1, that would also bring the half-life down. Just 3 is our steadiest, longest half-life. So now we're trying to move to 6.2. And there's a really easy shortcut. For each one step in pH, the half-life is divided by 10. So we'll just put 1/10 half-life. So we have a half-life of 9 months at 5.2. We're moving away from 3. So we're just doing 9 months over 10 equals 0.9 months. I don't know what 0.9 months are, but 3 to 4 weeks sounds right to me, right? It wouldn't be 6 to 7 years. That wouldn't make sense. It's not days. So there's really only one answer that makes sense here. This next one's kind of hard because in the past, he has given us these equations to where these are stepwise, right? So at 5 degrees, we know the half-life is 10 years. And at 25, we know it's 1 year. Meaning that for every 20 degrees Celsius, there is a factor of 10 difference. But if we're going to 35, we can't do a full factor of 10. What we can actually do to circumvent this is, since we know each one of these steps is multiplicative, right? When we're going from 5 degrees to 15 degrees, for example, there's something. Let's call this x. And from 15 to 25, there's another x. So that's essentially, since these are multiplied, this is x squared. So if we have a value of 10 here, we can write x squared equals 10. We don't really need to know what x is. We can just write that x is the square root of 10. And this will be our factor. So if we know our half-life is 1 year at this, I guess these are, I'm sorry. We're multiplying by x stepwise, but the half-lives are dividing. So I'll write those down here. So for example, we have 10 years here, unknown in the middle, and then 1 year. And then to get to 35, we're simply just dividing 1 year by the square root of 10, which I believe is 3.2. So that'll get us about 4 months, which is between 3 and 5. So again, if that doesn't make sense, I think he might change this problem again in the future. Our class did pretty bad on this, just for the sense that he will usually always give it in an increment you can do scalarly. So for example, I'm surprised in our year he didn't ask for a change to 45, right? Because that would be 5 to 25 is 20, 25 to 45 is 20, just to make it a little bit easier on us. And so again, he might change that for you, but this is how you would do it if you really wanted to do it mathematically. Each time it's divided, each 10 years it's divided by a square root of 10. And this is also different for every solution. I don't want you thinking because it's 10 years it's always a square root of 10. It varies in the solution. It's just whatever your scale factor is. Okay, so for the next problem, again, it's kind of just multiple choice, memorizing more or less. And what this problem really wants you to memorize is there's a question about this every year on the exam, and it's that hydrolysis is the most common form of chemical reaction to degrade things. This is just due not only from water in solutions, but also water vapor in the air. As for all these other ones, EDTA removes peroxides. I don't think that's true. I forget what it does do. Maybe it prevents hydrolysis or something. Changing the type of container does not affect the stability. That's not true. Why else would we have amber vials for things? And then this is a lot of kinetics. I think this has to do with decreasing the energy state of C will make AB less stable. That part is true, but this will decrease the shelf life. That's not necessarily true. Okay, yeah, so again, just some semantics in that problem. Some parts of it were true, but overall it was false. So for this next one, again, memorization. Every year it's going to ask about a drug suspension. You need to know there's pseudo zero order. Something that was actually really nice about this exam is Dr. Lee did not have us do pseudo zero order kinetics, so I hope you guys don't have to do that as well. There have been some problems with that in the past, but they are on some of the older exams. Essentially, those are just the ones that start out zero order. The way you solve them is you find out the time it switches from zero order, right, which is linear, down to first order, and then you can solve from there. So for example, if they're in the zero order region, you just solve through a linear equation. If they end up in this region down here, this exponential region, you solve up to the zero order region through the rate constant, and then you change it to a rate, which is probably something like e to the negative kt, right? So not too bad. And if he's not giving us, if he didn't give us problems on it, I can't imagine he does problems for you on it, just because for the newer exams, it kind of shows what content is moving towards, and if this is something that's kind of being phased out, I wouldn't worry about it too much. Which of these is true? and its hydrolysis can be different in acid and base forms. This makes sense, right? Because if an acid has a more, favorable thing to cyclize, maybe. So I don't know, maybe this is an acid versus a base. That can obviously change the kinetics. But I'll more explain why the other ones aren't true. I usually solve these through problem or process of elimination if you can't tell. Removing oxygen in container is used to reduce the rate of hydrolysis. This isn't true. When have you ever removed air from a container in a community pharmacy? Kind of just common sense. Again, it probably would work, but it's not commonplace. Enzyme is saturated. First order kinetics. K equals Vmax. This is not true in first order. This would be true in zero order because then it would be linear. But there is a Vmax you can theoretically reach, and this is a linear line. That's why I drew that, by the way. Buffer is added to change the pH. Buffer can be used because the degradation is only affected by pH and not buffer ions. This isn't true. Sometimes the buffer ions can interact with the solutes, so this one is B. This next one, you need to use a little bit of OChem. Well, technically not. You could memorize this, but which of these would undergo hydrolysis? Let's draw these really quick. We have an ester. All right, I see an oxygen and a carbonyl group. This could pop off, so that means 1 is potentially true. We have an acid chloride. This is a really good leaving group. Something else like water could, attack here. 2 is feasible. We have an acid, right, ROH. This does not have a good way to leave, or I didn't mean to star that. I meant to X that. This is not a good leaving group, right? I almost did it twice. Because it's only a single bond. There's no carbonyl to make that induction, so not a good leaving group. And then a ketone, same thing. Carbon bonds, so this isn't good to leave. So 3 and 4 aren't good, 1 and 2 are good, and that means our answer is A. So again, just knowing that water likes to attack at these sites where there are carbonyls. Carbonyls and kind of not a carbon, because right, even though there's a carbonyl here, there's also a carbon-to-carbon bond, which you may remember are very strong, so that's kind of why we don't destroy these groups. This last one, higher activation energy, does not have a higher rate constant usually. Usually it's a lower rate constant because more energy means there's normally like a higher temperature threshold, meaning the reaction will go slower. Higher degradation rate, again, kind of asking the same thing. Since it requires more energy, it won't be as fast. Degradation rate is less sensitive to effective temperature. This is wrong, kind of with what we were talking about before, right? You need more temperature to make the reaction happen, so it's actually more sensitive to temperature effects. So it's actually E. None of the above are correct. And then finally, last slide. Essentially just looking at each one of these reactions, seeing what they do, right? Usually the things we add are things going into our substrate, and the things that are minuses are the things taking out. So we want to see DEDT. So what's making E? We have K2, so CK2 should be positive. Here it is. And then also D goes into E with K4. So this should be plus D times K4. You can see here this is minus, so we already know it's wrong. And then this is actually taking out with F with K5, right? Because it's taking away from E. So this is minus K5F. But you can see that's not the equation. There was a minus here, meaning that D is wrong. All the rest of these were right. A final problem. A really kind of interesting way to think about this, I saw this on Dr. Lee's answer key, was we know the shelf life is 1 week, so the 90% half-life. So if we have 1 week as our T.9 is equal to our K value, which is our degradation rate, which we don't know, and then our concentration, we can actually model these equations. We could do kind of a substitution. If we know that we want to double our concentration to 20 milligrams per milliliter from 10 milligrams per milliliter, we could do 2CO over K. And then we don't know how many weeks this would take. But since we know we multiplied this side by 2, right, because we doubled that initial concentration, we know we need to double this side of the equation as well. So 1 week times 2 is 2 weeks. And that's just balancing an equation, right? Because this we know to be true, just by the definition of what like a shelf life is. So we know shelf life, I'm just going to write that as SL, is equal to concentration over rate constant. So 2 times concentration would just mean 2 times shelf life for 0 order, and that's 2 weeks. But with that, that was our exam 3. I hope this helped. I hope it made it simpler in some places, or if not, at least showed you kind of what you need to go in the notes for. Again, this equation's kind of a balance of memorization and math. So the math was mostly at the beginning. I would practice that more, and then for the memorization, I would just do the old practice test, maybe once or twice. Again, seeing me do it is probably helpful, but you'll probably memorize it more if you just go through and circle yourself as well. But with that, good luck on the rest of fundamentals. Like I mentioned before, I already do have the video for your final posted. Your final, at least for us, was cumulative, so you could go back and review the last 2 videos. But the new material that you'll be getting with Dr. Kumari, I do have a separate video for that, and that is most of the final exam, so I would highly recommend watching that. But yeah, thanks so much, and I'll see you in the next one.